All right, so I think this one's a lot of fun. We have polynomial multiplicities. The other day we talked about end behavior, and that's talking about what's going on at the ends of the graph. Multiplicities kind of helps us with what's going on the inside of the graph, and we want to know what's going on the outsides and the insides so that we can eventually sketch the graph. Now, our little reminder here, a zero of a polynomial corresponds to the x-intercept of the graph of the polynomial. Okay, and then we should also kind of note here that these words are synonymous. We've got x-intercepts and zeros already, and later we'll also call them solutions, and sometimes they're referred to as roots. And we're running out of room. Okay, so what is the multiplicity of a zero? Well, the multiplicity of a zero is just the number of times that zero appears, the number or repeats, I suppose, the number of times a zero repeats in a polynomial. For example, determine the zeros of the polynomial and their multiplicities in the following function. So you can see here that we are already in factored form, which is kind of great because this would not be fun to look at in standard form. It would be very long. But as we've discussed in a previous lesson, each of these has a potential of being zero, and I can find that out with inverse operations. And through enough pattern recognition and repetition, we found out that the opposite sign of whatever's in here is usually what's going on, as long as there's no number with that x. So that means I've got x equals -5, I've got x equals -2, I got x equals +1, and x equals +5. So these are all different zeros, which correspond to x-intercepts of the graph. Now, you'll notice that each one has an exponent on it, even if there isn't one there, right? We've got an exponent there. It's a 1. That is the number of times that factor repeats. So, for example, the multiplicity of x equals -5 is 3. So we would say with multiplicity 3. And here we would say with multiplicity, and that's a really long word, I don't want to write it out. So for, here we would have multiplicity 2, and this was just multiplicity 1 because there's only one. It's not multiplicity 0 because it's not repeated, it still occurs one time, okay? For example, take a look down here. This one looks a little bit different. We have a little x out here by itself. This one, we can see that x is equal to the opposite of that. We've got +3 with multiplicity 2. Here I've got x equals -1 with multiplicity 1. And what about that guy? Well, remember the zero product property, right? If this is like a times b times c equals 0, then one of those things has to be 0. Either a is 0 or b or c. Well, we set each one of these equals to 0 and solve. What happens if I set x equal to 0? It's already solved. So that's got multiplicity 1. Just a note there. If you've got an x all by itself, then the multiplicity of that, or I'm sorry, then the solution for that particular value is x equals 0. All right, this is my favorite part. So you'll see here we've got 4 different graphs with 4 different equations. And each of the equations has something in common. They all have a factor of x plus 6 and x minus 7. You'll see that in each of these. The only thing that's different is the multiplicity. Here they have a multiplicity of 1. Here one of them's got a multiplicity of 2. Here this one, the other one's got a multiplicity of 2. And here they both have a multiplicity of 2. Now I want you to pay attention to the shape that the graph makes as it passes through each of those corresponding zeros. What do you notice? Well, I would hope that you noticed that some of these look like straight lines and some of them look like little parabolas. And that's what the multiplicity on a graph tells us. If the multiplicity is 1, it will pass through like a first degree polynomial, a polynomial of degree 1. That's a linear equation, straight line. If the multiplicity is 2, well, what is that shape? That's a parabola. It would look like a parabola at that x-intercept. Like here, if they're both 2, they both look like parabolas. Okay? So here we have a 2 and a 1, so we have a parabola and a line. So this is basically just a summary here. If I've got a first degree polynomial or a multiplicity of 1, then it will pass through like a line. Now, the second degree will also be the same for fourth degrees, or all of those even degrees, just like when we talked about end behavior, the ends will go the same way. So you'll get one of these two possibilities. Now with the third and the fifth and the seventh, this is a little bit different. It'll look like kind of like a parabola, but one end of it is turned. Okay, and that happens for the same reason that end behavior does that at the ends, because with the even powers, with those negative numbers, when you multiply negatives, negative times a negative is a positive, so you get both sides going up. Here, when you multiply a negative number an odd number of times, that left side's still going to be negative, so that other side stays turned down instead of flipping it back up. So that's multiplicity.